Hello ladies and gents, just wanted to give you a quick video review of topic 4 and topic 9 for those HL kiddos out there. As you can see here ladies and gents, the standards for topic 4 are quite impressive. There are a lot of them. So take a moment and familiarize yourself with them. As we go through this video, we will be reviewing most of these standards. I may miss a couple, but here they are for your reference. So here, ladies and gents, we have the topic 4 vocabulary words. These are really important for you to make sure you have a good grasp of because they do refer to different things. Some of these, a good portion of them, refer to characteristics of waves. Some of them refer to things that waves can do, and one of them refers to a very special situation that can arise when we have waves interfering with each other. So please make sure you're looking at this list. It's really important you understand it as we move forward for the review. After we have a good grasp on the vocabulary for topics 4 and 9, we really need to make sure we sit down and pay attention to the most important concept, simple harmonic motion. SHM is a very specific type of motion for when an object is at a fixed position. So if we have an object at fixed position X, as this object moves away from the position, it experiences the restoring force. The restoring force always points back towards this fixed location and is proportional to its distance. So the farther away the object goes, the more force it experiences. So particularly for those HL kiddos out there, I want to make sure I talk about the relationship between circular motion and simple harmonic motion. One of our first occurrences or documentations of simple harmonic motion was using circular motion and a three-dimensional plane projected onto a two-dimensional surface. So as you can see here, as the object goes around on the turntable, its movement from left to right is documented on the piece of paper over time. This is really important because if we remember last year, this is how we were able to create very specific equations of motion for position, velocity, and acceleration. Now, depending on your starting position, either here, position number 1, or here, position number 2, it actually changed the value of this, all right? And this was either going to be sine or cosine. So depending on our starting location, we used either sine or cosine in this equation. Taking your derivatives would then affect the corresponding equations for velocity and acceleration. Here you can see a little bit of a documentation. We took x of t to be sine of omega t, our angular frequency multiplied by time. This allows us to start when the object is passing through the middle of the motion. It's not at one of the extremes. It's not at its maximum displacement. It is at its center. All right, it's at its fixed position. Using these equations, we were also able to create a new one that calculates velocity not based on time, but based on the position or the distance it's traveled. Here we can see the relationship of these three equations for both SL and HL. This is really, really important. Please make sure you're observing time period T. Each of these is one full period, and you can measure that in different ways as shown here by these diagrams. We can measure through the centers. You have to measure 3 centers to get a full period or a full wavelength. You can also measure from peak to peak. Okay, so these are the two methods that we generally use. Let's do some really quick practice with this, ladies and gents. Pause your screens, and when you unpause, the answers will be. We also have to remember that energy shares a cyclical pattern when it comes to simple harmonic motion as well. Potential energy and kinetic energy are constantly canceling each other out to give us the same sum of total energy. As a wave travels through a medium, there are 2 different ways in which it can do it. The oscillation of energy can go in the direction of motion, or what we call a transverse wave, or the energy can oscillate perpendicular to the direction of motion, which is what we call a longitudinal wave. So a great example of a transverse wave would be sound, and light would be a great example of a longitudinal wave. Sound is an incredible example of a longitudinal wave. As sound is created at a source, it creates areas of compression and rarefaction. So the areas of compression are these areas where we see particles of the fluid or the air clumped together. Now, there is some specific terminology you should know that's listed here for frequency and amplitude. When we do say frequency, we mean the pitch, and amplitude refers to the volume in sound. Light, however, is the exact opposite. As we can see here, as the wave travels from left to right on the screen, the electrical and magnetic waves are moving either up and down or in and out of the page. They are perpendicular to the direction of travel. Now, light has lots of interesting properties, but most importantly, it has the speed limit of 3 × 10⁸ meters per second, and that was defined by Maxwell back in the 1800s. This is the universal speed limit and is the basis for lots of other ideas and theories in physics. Now, as waves travel, whether they be sound or light, transverse or longitudinal, they all follow this general rule right here. The intensity of the wave decreases at a 1/r² value. So as you can see here from the drawing, as we look and as light travels, it spreads outwards. Well, if light is made of a certain amount of energy, as that energy travels, it spreads. So the light does become a little bit weaker as it begins to cover more area. Once the waves are traveling through a medium, they can go through the phenomena of superposition and interference. So if two waves have a similar amplitude and similar frequency, they can create interference. As the waves pass through the same place at the same time, their amplitudes can add to each other, creating constructive interference, or they can subtract from one another, creating destructive interference. It is really important, ladies and gents, that we understand the key aspects of this phenomena. When we have constructive interference, the peaks of the wave are lining up with each other. If you look at our example right here, we can see that the peak of one wave lines up with the trough of another wave. When you plot them on the same place, they cancel each other out. So this alignment of the two waves is what's most important when it comes to superposition and interference. Here you can see a wavefront diagram of two sound waves interfering over a specific area. The next phenomenon of waves we need to talk about is refraction. Refraction is what occurs when light enters a new medium. Entering a new medium causes light to bend. The direction depends on the density of the new substance. If we go from more dense to less dense, we bend away from the normal. If we go from less dense to more dense, we bend away from the normal. This phenomenon is essential for total internal reflection. Total internal reflection is this idea that at a certain point, going from more dense to less dense, the light will not exit the material. And this is actually defined very, very well in Snell's law. Filling this in for critical angle, we see that we can easily create a relationship or ratio with the initial angle or the critical angle and the ratio of indices of refraction. From this point on, ladies and gentlemen, past the critical angle, the equation becomes undefined. One of the coolest side effects of refraction is the dispersion of light. Because each wave has a different amount of energy, it actually figures that when they enter a new medium, they refract differently based on the amount of energy of each individual wave. So the more energy you have, the more drastic your angles or your refraction is going to be. And that's what creates the prism of light, or that's how prisms are able to break light apart. Polarization is another amazing phenomena that we take advantage of all the time. Because light is made of both an electric and magnetic wave, we can take advantage of this by only allowing energy oscillating in one direction to come through. When we do that, we eliminate half of the intensity. So if you remember Malou's law is specifically about objects coming between not just one, but two polarizers. And Malou's law tells us that the intensity is equal to the original intensity times cosine squared theta. Please remember, ladies and gents, this original intensity is after it comes out of polarizer 1. All right? So please make sure you remember that for IB questions. This is really what polarization is, ladies and gents. We can dictate the direction that the light waves travel. Are they vertical or are they horizontal? Whenever you do that, you eliminate half of the intensity. But if we put those two things together, you can eliminate all light passing through. The last phenomenon we have to talk about is standing waves. Standing waves is really superposition and interference that is happening on a continuous scale. So similar to superposition, we need our waves to have the same amplitude and the same frequency and traveling in opposite directions. Now, if we can repeat this process because of boundary conditions and waves bouncing back and forth through the same medium, we can create standing waves. Now, we need to be very, very clear here, ladies and gents. There are different types of situations and different types of boundaries that we have to consider. So the first thing we want to consider, ladies and gents, is the tube. The tube has really two different type of boundary conditions. You can have what is called an open tube, or you can have a closed tube where it is blocked off at one end. You can also have, ladies and gents, strings. Strings can either be torn or taut between two fixed locations, similar to a guitar, or you could have a string hang and you could have one loose end and one bound end. Okay, so please make sure, ladies and gents, that as you're looking through these situations, we have to identify the geometry and we have to identify the boundary conditions. So these boundary conditions are really important because waves reflect off of surfaces. So when we have something, for example, a string that is bound at one end, as the wave approaches the fixed end of the string, the wave does not simply reflect backwards going with the same positive amplitude. Instead, it flips itself and is now going back with a negative amplitude. This phenomenon right here is what helps us create the waves traveling in opposite directions. Building off this idea of standing waves is the concept of resonance. Resonance says that every object has a natural frequency of vibration to the system. So for example, when you tap the rim of a glass, it gives that nice ching. This is the resonance frequency based off the geometry, based off the boundary conditions. When we create that driving force or frequency, the object resonates and amplifies that sound. Here, ladies and gents, is a nice review. This information is not given on an IB study guide, but it is very, very nice to know, ladies and gents. I highly recommend that you just commit these kinds of things to memory, or if you want, derive them based off the geometry that you see. So next up, ladies and gents, we got to get onto some of that HL content, like the Doppler effect. So the Doppler effect is really interesting. It can happen to all types of waves, but essentially the idea here is that the source or the observer is now moving. So if the source or the observer of the sound moves at a decent percentage or fraction the speed of the wave, we actually create an effect like you see here in the diagram. If two objects are moving closer to each other, we see a crunch of the waves. We see the wavelength get smaller. If the objects are getting farther from each other, we can see the wavelength of the waves gets bigger. We call this red shift and blue shift. Red, because the wavelengths get bigger, and then blue shift, because the wavelengths get smaller. Therefore, shifting the light more towards the red end of the spectrum, or shifting the light more towards the blue end of the spectrum. Okay? As you can imagine, we're talking about objects that are emitting light. We are talking about stars. That's where this idea first came around. But you have experienced it as well. You've experienced it with ambulances, police cars, jets, or planes. Any type of large object that is coming towards you has generated the Doppler. The reality is that the Doppler effect only has one equation. We separate it out for convenience, but this is the actual equation for the Doppler effect. The confusing thing about the Doppler effect is when do we use plus and minus. So here's a little drawing to help you understand when you're going to use that. F naught represents the frequency of the source. F represents the frequency of the observer. So here you can see if the source is moving towards the observer, we get negative. If it's moving away from the observer, it's positive. If the observer is moving towards the source, it's positive. If the observer is moving away from the source, it's negative. Of course, ladies and gents, when I say positive and negative, I really mean add and subtract. So pause your screen, ladies and gents, and the answer will show up in a second. As we move on to our next topic of diffraction, these two definitions are very, very important because they're used quite often in these experiments. When doing diffraction experiments, we like to use light that is monochromatic and coherent. All right, monochromatic is light that is of a single wavelength, so typically coming from a very particular source like a laser. Coherent light is light that is monochromatic and is in phase. So we have multiple light beams that are stacked on top of each other, and the peaks and troughs of these different waves are all in sync and in phase. After last year, we were able to develop a pretty good definition of diffraction, and we have to remember that it doesn't only happen when light passes through a slit, but when any wave passes through a slit. So the reason we want to keep that more general definition is because we can apply the idea that d, the distance of the slit, or the size of the slit, should be about the same size as the wavelength. When we approach this relationship, we achieve maximum diffraction. Here's a result of single slit diffraction. We see a peak maximum followed by minimums, and every maximum afterwards gets weaker and weaker and weaker. You'll also notice that from our general formula, all we have to do in order to find these other minimums is simply multiply by the letter n, right? N standing for this order of maximum. Is it the first order or is it the second? Is it the first dark spot or is it the second dark spot? That's what n represents. Here you can see a nice reason why we like to use monochromatic light. While using white light is a very interesting pattern, it becomes much more difficult for us to measure and see the dark spots. So here's a really interesting relationship between single slit and double slit diffraction. Here you can see the single slit diffraction represented by the dashed line, right? It creates what we call the diffraction envelope. When we add a second slit, the new resulting pattern fits inside a single slit diffraction pattern. We do create more maximums and more minimums, but they still fit within the original pattern. Here's something specific for those HL peeps. Please make sure you know about the geometry and math behind two-slit diffraction. When we are doing two-slit diffraction, our equation tells us the distance to the next bright fringe, not the next dark fringe. And the equation is a little bit different, so please take note of that. The final thing that we can talk about with diffraction is the idea of resolution. This is another one of those bigger HL topics, but it is still really, really interesting. How can we distinguish two objects that are emitting light as they pass through a slit? How does a camera tell apart two different sources of light? Well, it has to do with the geometry. As you can see from the drawing and the equation, the size of the aperture is one of the biggest pieces of the puzzle. We also like to use this situation to solve for the distance that objects are away from the aperture. So creating these right triangles allows us to solve for how far apart those objects are from each other and how far they are from us. For these next two slides, ladies and gents, go ahead and pause your screens, and after a couple seconds, when you're ready, unpause, and the answers will be there. Go ahead and pause again, ladies and gents, and the answer will come up.